Okay. Hi everyone, this is going to be a video walkthrough for question 3 on exam prep week 11 on graphs. Okay, so a preface before diving into this problem. This problem is fairly difficult, so no worries if it didn't come to you because this problem took me a really long time to solve. Okay, so the problem states, for each of the following scenarios, write a brief description for an algorithm that finds the MST. Okay, and then the first scenario is that all the edges have edge weight 1. Okay, so if we have any graph, and let's say all of these edge weights are the same, it doesn't really matter which edges we choose to include in our MST, as long as we choose n-1 edges and everyone is connected, right? In other words, this is a valid MST because all of the vertices are connected, there's no cycle, right? But on the other hand, this one isn't a valid MST because there's cycle and not all the vertices are connected, okay? But there might be multiple valid MSTs, right? Like this is also a valid MST. So given any graph that has all of the same edge weights, we notice that the MST isn't too hard to make. All we need to do is just figure out if there is a spanning tree in the graph, and then we just return that spanning tree, okay? So solving this problem reduces into just given any graph, how can we find a tree in that graph that spans all of the vertices? So to find a tree in any graph, we can run DFS. So the answer is we run DFS to get a spanning tree, and then we output that. Okay, so I'll give you guys a quick walkthrough of DFS. So how DFS works is we start some vertex and then we just kind of walk along the graph, breaking ties in some manner. So let's say that this is the graph we get by running DFS, or the tree, right? Because DFS produces a tree, that's how DFS works. So we know the tree the DFS produces, if the graph is undirected and connected, must span all of the vertices, because for any graph that's connected, DFS will find some tree that connects them all, okay? So this tree doesn't necessarily need to be like unique. We just know it's a tree that connects them all the edges are the same, it must be the MST. Okay, so let's move on to part B. For part B, we notice that now the edges can have two possibilities, edge weight 1 or edge weight 2. So it complicates things because we can't just run DFS on the whole graph. That doesn't necessarily work, right? Okay, so given this graph, right? Let's just create a random graph. Okay, I want to make it a pretty big graph for this example. We're going to try to brainstorm together how we can solve this problem. So let's add in some edges of weight 1. Okay, that seems to be, actually, let's add. Okay, let's add the rest as weight 2. I'm just creating some example that I could try to figure out an algorithm for. So this is a tough problem, and the way I like to approach these tough problems is just by how would I solve this, just looking at the graph and somebody told me, solve this problem, don't use a computer, okay? What I'd probably do is I'd say, let me first add all of the edges of weight 1, because those are prioritized over edges of weight 2 in a potential MST, okay? So we'd say, okay, we can't add this edge 1, right? This one can't get added because it would create a cycle. Then we would add, let's just say these two, right? And then we would add this one, okay? So the next step would be, okay, we have these kind of 3 connected components, right? We have these connected components. All we need to do is figure out which edges of weight 2 we can use to connect them, okay? So the next thing that I would do if I'm just intuitively running it is, okay, we just need a few more edges of weight 2 to connect these connected components. So let's just arbitrarily choose this one and this one, because we also have this mini connecting component in the middle. And then we also have this one, right? So we see that a potential algorithm, just like some intuition, is first do something to all the edges of weight 1, then we have a bunch of connecting components, then connect these connected components together using the edges of weight 2, okay? So with this in mind, I'm going to formalize an algorithm to solving this that builds off this intuition we've built so far. So the first thing that I'm going to do is remove all edges of weight 2 and run DFS to create a bunch of connected components. Okay, so let's see what I mean by this. I'm going to get rid of these yellow edges. Okay, there's so many. Let me quickly get rid of these yellow edges. I want to start from the initial state. Okay, perfect. So what I want to do first is remove the edges of weight 2 because we kind of want to add them after we add all the edges of weight 1. Okay, so let's see if I can quickly isolate all of these, and I'm just going to change the color for the time being. Perfect. Okay, so now assuming these edges of weight 2 just like don't exist, let's run DFS and create a bunch of these mini connected components, right? We can run DFS on a graph that isn't fully connected. What we will get is a bunch of these mini connected components. So what that means is we'll get this, this, and this. Okay, so now after running DFS, notice that we have 4 connected components. 1, 2, 3, and 4. Let's call these A, B, C, and D. Okay, so now we can kind of think about these. Let's just treat each connected component as a node, right? All we have to do is we have these 4 nodes, A, B, C, D, so we can just run DFS on these big nodes using the edges of weight 2. That's the next step of the algorithm, but I'll make it more official after writing it down. Okay, so convert each connected component into a node, bring back the edges, the 2 weight edges, and run DFS. And truthfully, the solution does a better job of explaining this than I, but I will give a good job with this example to explain what's actually happening. Okay, so if we have this graph, what we're going to do is we're going to convert it into a new graph where A, B, C, and D have been replaced with just nodes. Okay, so now instead of A, B, and C, and D, we're just going to have some nodes. Okay, we will have an A node, a B node, a C node, and a D node. Okay, now we need to bring back the edges of weight 2. Okay, so what I'm going to do is iterate through all of the edges of weight 2, and we notice that there's like could be a multiple connecting A and B together. So if there already is an edge connecting A and B, we just don't need to redundantly add another one. Okay, so being a little more official about this, let's find a cool color. This dark gray looks good. So let's just like iterate through these edges. Let's say this first edge right here, let's add that. Okay. So now we go to this next edge and we say that A and B are already connected, so we don't need to add that to this new graph that we're making. Okay. So then we repeat this process, and let's say that we end up with, okay, we end up with this graph, right? And we can kind of ignore these other edges because they're a little redundant. Okay, perfect. So now that we have this graph where all I did was convert each of these connected components from the initial graph into its node, and then I removed the excess edges of weight 2, right? Now that we have this graph, in order to figure out which edges in this graph to the left of weight 2 that we should add, all we need to do is run DFS on this graph, okay? So after running DFS on this graph, let's say that we get this. Actually, if we wanted to run DFS breaking ties alphabetically, let's just do that. We'll get that. So now that we have these edges of weight 2, let's go back to this graph and we can actually add those in, right? So this one, let's do them in green, right? This edge corresponds to this one right here. The edge from B to C is this one right here. And then we took this one from C to D. So that is the algorithm. Just to give a quick recap, all we're doing is we first remove all the edges of weight 2, then we run DFS and we get a bunch of mini connected components, right? Each connected component you guys can maybe think about as a mini MST. So with these mini MSTs, we need to connect the mini MSTs together. To do that, we'll create a new graph where a node A in the new graph was a connected component from the previous graph. Okay, so given that connected component, what we'll do is we will bring back the edges of weight 2, right? If there's a redundant edge of weight 2, there's no point adding it. For simplicity, we won't. Then we will rerun DFS using this new graph. We will get a subset of edges of weight 2 that we will then add back to our graph from before, and we will get our final MST, which is about to be highlighted in blue. Right? Okay, so that is all for this discussion walkthrough. I hope you guys found it helpful. And yeah, see you guys.